First thing we want to do for any of these problems is go ahead and create our area model. That can help us. You don't need to do this if you're feeling good at factoring, but I think this is probably the easiest way to look at it. And we can say, okay, there's an x times an x, that equals x squared. There's also a -9 here. So this is going to have to be +3 minus 3, so that way I can get a 0x in the middle. So I can get a positive 3x and a negative 3x. All right, so this problem is going to simplify to x plus 3 and x minus 3. And another thing we talked about yesterday is this is called a difference of squares problem. When there's no middle number, you can just say, I'm going to take whatever the last number is, and I'm going to square root it, and I'm going to do plus that square root of that number and minus the square root of that number. This is the only problem where it looks like that applies for this problem set. All right, so problem 2, this one looks like it's going to be more of just a traditional factoring problem. I have x squared minus 8x minus 9. And usually when I see an 8x minus 9, like the factors 9 are 3 and 3. Well, we just did 3 and 3. That's not going to work. Or the other factors are 9 and 1. So I'm guessing one's going to be -9 because that's the bigger number. One's going to be +1. And sure enough, that gets me a -8x in the middle. So this one comes out to x plus 1 times x minus 9. That's our factored form. Problem 3, I have a common factor of x in both terms. So for this one, factored form is really just going to be x times x minus 7. I can pull out x out of both terms. And now I've got like an x minus 0 times an x minus 7, basically, is what it looks like. All right. Problem 4, set up that box method. It's a +8, so that means both the signs are probably going to be negative because it's a -6x in there. So the factors are 8 and 1. If I did -8 and -1, I'm going to end up with a -9 in the middle. So it's not going to be that. If I did 4 and 2, I'm going to get a -2x and a -4x, and that'll give me a -6x. So that's perfect. So it'll be 4 and 2. So x minus 2 and x minus 4. That's how we're writing these in factored form. And notice that I started with a second degree polynomial, and I ended in factored form with a second degree polynomial. There are 2 x's down there as well. Problem 5 and 6. These ones are the toughest ones. And I think just because you have that 3x squared at the beginning, I think that makes it a little tougher. So I really like the box method for these problems, because I can start by saying one of them is going to be a 3x, one of them is going to be an x, because 3x times x is 3x squared. Now for the other box, the 4, I can say let's multiply by 2. So I could do like a -2 and a +2 or something like that. That's one possible factor, or a 4 and a 1. Looking at it quickly, if I tried 2, I like this because I get a -6x and a +2x. So I got it on my first try this time, but I ended up getting that -4x in the middle. So this is perfect. This one's going to be 3x plus 2 times x minus 2. There's my factored form. All right. And then the very last one here on the warm-up. This one looks kind of scary. It's got the 2x squared, the 5x, and the 7. But one thing I like about this one is, what's a -7? The 2 and the 7 are both prime numbers. So that means it's either going to be 2x like plus 7, or it's going to be 2x plus 1, something like that. So the 7 and the 1 can only be on one side or the other. You can switch pretty easily. So this one's not a hard one to double check, I think. So -1 times 2x is -2x. 7 times x is +7x, and that gives me a +5x. So again, I got that one on my first try. So this one simplifies to 2x plus 7 times x minus 1. There's our factored form. So we got to be really good at writing in factored form. That's what we're going to be working on the next few days. And we started working on that yesterday even. But the whole idea is that we're trying to get down to factored form. So once we do our division to get down to a quadratic function, now we should be able to factor, and that'll be a lot easier than doing division one more time. Most of the time, that's easier. All right. Worksheet 24 today is the rational root theorem. Okay. So what we're going to focus on specifically today, we're going to find all the real zeros of a polynomial when the a value equals 1. And what that means is the leading coefficient is equal to 1. So we're going to say that equals 1 right there. Something like that. All right, so what we're going to be doing today, the rational root theorem, the way it looks is it says what we need to do is we need to identify the constant term, which is always going to be the very last number, and we need to identify the leading coefficient, and the leading coefficient is this a sub n here. All right, so if f of x has integer coefficients, all right, that just means no fractions, then every rational zero, we're going to call these rational zeros. All right, these are zeros that we can find. Is going to be this p over q, where p represents the factors of the constant term, which in this case is a sub 0, and q represents the factors of the leading coefficient. And we'll put this into perspective so it makes sense for you guys in a little bit. And that's a sub n. So let me highlight them real quick. There's a sub 0. There's your a sub n. Okay, so real quick, because this is the rational root theorem, so we're saying every rational zero of f has the following form. Well, what does rational mean? Rational means a number that can be expressed as a fraction. Okay, a number that can be expressed as a fraction. That's a rational number. All right, so what this rational root theorem is saying basically is if we start with something in standard form, it doesn't matter what's going on in the middle. We don't really care about anything in the middle, the dot, dot, dot. Not a big deal. We're looking at the very end, which is a plus 15. And we're going to look at the very beginning, which is a 1 x to the 4th. And today we're only going to do examples of 1. We're going to look at examples other than 1 on Thursday this week. Okay, so we know that this the factored form will be written as this: f of x equals x plus a, x plus b, x plus c, x plus d. We don't really know what a, b, c, and d are yet, but because it was x to the 4th power, it's going to be written as 4 separate factors. So there's 4 x's down there. Okay, that's the first thing we notice. What we want to show, though, is that a, b, c, and d will all multiply together to get us positive 15. That's what the rational root theorem is telling us. Whatever those a, b, c, and d values are, they're all going to multiply together to get us positive 15. If we look back on our homework from last night, we should be able to do that at the end of our factors. We should be able to multiply all the factors together. That any polynomial that had a leading coefficient of 1, you can multiply all the factors together, and you're going to get that last number in standard form. All right, and we'll take a look at that today a little bit too. We'll multiply things back together at the end and double check it. Right? Another way of saying this is that A, B, C, and D are factors of 15. And 15 is the constant term, A sub 0, from the general form f of x from the box at the top of the page. All right? So now, the possible integer factors of 15. All right? The possible integer factors are 1, 3, 5, and 15. Right? But there's actually more than just that, because to get a positive 15, I could multiply positive 1 times positive 15, or I could multiply negative 1 times negative 15. So technically all these numbers could be positive or negative. I could also say positive 3 times positive 5, or negative 3 times negative 5. So it's important to remember that there's a plus or minus in front of each of these possible integer values. All right, so there are 8 possible integer factors. Of positive 15. And what that means is we could have a lot of different ways to write this out when you factor it. If we don't know what the stuff is in the middle, which we said with the blue, we don't really care about it right now. What that means is when we write these out, we could write them out a few different ways. We could say something like x plus 1 times x plus 1 times x minus 1 times x minus 15. As long as they all four numbers multiply out to be a positive 15. Here I've got a positive 1 times 1 is 1, times negative 1 is negative 1, times the negative 15 is a positive 15. That's what I mean. So there's a lot of different ways we could write this out. I could say x minus 3 times x plus 5 times x minus 1 times x plus 1. That's another way to write it out. And that would be true as well, that I would have all these numbers multiplied to give us positive 15. I could write it out as x plus 15, x plus 1, x plus 1, x plus 1. I could write it out as x minus 15, x minus 1, x minus 1, x minus 1. As long as all of them multiply together to ultimately get us positive 15. All right, and then there's x plus 5, x plus 3. This is another good example. X minus 1, x minus 1, something like that. All right, there are a lot of different possible outcomes. This right here is only a list of 4 potential outcomes. All right, so there could be a lot more than just this. Okay. So there are also non-rational roots, and I have it down here written, the zeros could just as easily have been plus or minus root 3, plus or minus root 5, plus or minus root 15. All right. And you could still technically multiply non-rational roots together to get you positive 15. All right. Each of these roots would appear in pairs. And together, each pair is called a conjugate pair. And this is where that difference of squares thing comes into play that I talked about. So maybe we simplify this equation and we end up getting something like x minus 5 times x plus 1 times x squared minus 3. Right now I have 1, 2, 3, 4 x's, but it's not quite simplified all of the way. I have a difference of squares problem, and this is where the non-rational roots come in. I can square root 3 and write this as x plus square root of 3, x minus square root of 3. And that could still work as a possible foursome for a factored form for what this equation could look like. Because positive square root of 3 times negative square root of 3 is going to be negative 3. And then I can do negative 3 times negative 5 is positive 15 times 1, and I still get positive 15. All right, so that's another possible way I could write this out, is using that difference of squares thing that I've talked about as well. All right, that we might remember from AGS2 last year. Hopefully we do. All right. Now, what I want you guys to do is just like how I did it with the 15 up here. I listed all the possible zeros of 15. I want you to do that here. I want you to list the possible rational zeros for each of the following functions. All right, so that means you need to identify the last term. All right, and then what are all the possible factors and how many possible zeros are there? All right, so take a minute and see if you can identify those two. So yeah, whenever we write one in factored form, no fractions allowed. So you can't have like x minus 1/2 or x minus 3/2 or x plus 5/7. You can't have that. You have to write it a little differently. All right, and we'll take a look at an example together and we'll talk about it. Okay, I'll talk about that no fractions in a second here. Let's see. Actually, you know what? We'll talk about it right now. So no fractions, what that means is we'll say like if x equals 1/3 is a 0 of the fraction, what that means is we would say like x equals 1/3, we subtract 1/3 from both sides. X minus 1/3, you cannot write this as a factor. Because we don't want a fraction in factored form. So what we do instead is we say, let's multiply both sides by x, or by 3, I'm sorry, and then let's subtract 1 from both sides. So we get 3x minus 1 equals 0. And that's, okay, that's the factored form we want to see. 3x minus 1 is a factor. Again, I just made up these numbers, but that's just an example. If x equals 1/3 is a 0, then 3x minus 1 would be how we write it in factored form with no fractions. All right. Okay. Now let's try this rule. What we're going to do first, we're going to write this in factored form, and we're not given any zeros at all, but we're given the number 20 as our coefficient at the very end. So we know all the factors need to multiply to give us 20. So the possible factors are 1 and 20, 2 and 10, 3 and nothing, 4 and 5. There we go. So there's 12 possible zeros here. That's a lot of options. So what we need to do is we would honestly just need to say, let's try and divide by 1 and see if it's a factor. So I'm going to use synthetic division here, and I'm going to start with the number 1. I'm just going to start with the positive 1 here. And the possible synthetic division numbers are going to be 1, -8, +11, and +20. And if this is a factor, I should get the number 0 over here. If 1 is a, that's why it's called a 0. If 1 is a 0, I should get a 0 at the very end of my polynomial long division. So first I drop number 1 out. I do 1 times 1, and then I add the -8. I get -7, -7. 11 minus 7 is 4. 4 I end up getting a 24, not a 0. So positive 1 is not a 0 of this function. We just proved it. So then what you would do is you would say, well, let's try another one. And we just start again. Let's try negative 1. I mean, this is literally how you would try and prove something as a 0. Is you just have to like kind of guess and check. We just kind of go through and figure it out. All right, so negative 1 times 1 is negative 1. That gives me a negative 9 there. Gives me a positive 9, positive 20, negative 20, 0. Perfect. So I just divided by negative 1 as a 0, and I found 1. No remainder, that's a good thing. So x equals negative 1 is a 0. And what that means then is if it's x equals negative 1, I could technically add 1 to both sides, and x plus 1 is a factor. So I can rewrite this as x plus 1, and then my other numbers here, the 1, the negative 9, and the 20, that's going to be x squared minus 9x plus 20. And that's one step closer to factored form. And now with the x squared minus 9x plus 20, I could write that in an area model and simplify it. That's what we did in the warm-up, and that's why we did it in the warm-up, because now we're simplifying the next step. All right. And it turns out we should end up getting, looks like it's going to be a negative 5 and a negative 4. So x minus 5, x minus 4. I don't have enough room to put an area model on my paper here, so I'm just going to show you guys what it comes out to. But that's the idea. So it's a use area model, but I'm out of room. All right, and that's our factored form. And notice it started as a degree 3 polynomial, and it's got 1, 2, 3 x's. Then all the coefficients need to multiply with 20 to positive 20. So negative 1 times negative 5, or positive 1 times negative 5 is negative 5. Negative 5 times negative 4 is positive 20. So it all checks out. Everything seems to make sense. So that's what factored form looks like. We can double check it a few different ways. All right. I think the hard part, though, is kind of at the beginning. I had to guess and check. I had to try a positive 1, prove that's not a 0, and then I tried a negative 1, and it turns out that was a 0. All right. So that seems to be the key to being successful in these types of problems. All right, let's look at another one here together. This one has an 18, negative 18. So the possible outcomes, or the possible factors, are 1 and 18, 2 and 9, 3 and 6, all right, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible zeros. Just so you know, when this is x to the third power, the most zeros this problem can have is 3. Or that's how many zeros this problem will actually have is 3. There are 12 possibilities, which means if I try the polynomial long division, 9 of those will not be factors. 9 of them will not work, okay? But 3 of them will, okay, if these are rational zeros. Does that make sense? So there's 12 possibles. Only 3 of them should be actual zeros. So the odds of me picking the correct one at the very beginning are not very good. Okay? Not very good at all. but I can do better than that. I can beat those odds. What I'd want to do is I would want to go to Desmos. So that's what we're going to do right now. This is going to save me some work, you guys. It's a little shortcut, and it's a totally legal shortcut. We are allowed to do this. We can graph this problem right here. All right, there's my problem graphed. And I can find all of the zeros. There's x cubed minus 2x squared minus 21x minus 18, and I can see all my zeros. There's a -3, a -1, and a 6. So x equals -3, x equals -1, x equals 6. I'm going to write those down on my paper. Those are the actual zeros. Okay, -3, -1, and 6. I'm going to make a note. Okay. I got these from graphing. All right, so you're allowed to do that. That's perfectly fine. You can find the zeros by graphing. But the purpose of these problems is you got to show me algebraically you know how to find them as well. So you can do that, but you still got to show me, hey, I know how to do this algebraically, Mr. Street. Once I have the -3, though, I can say, let's just go ahead and do division with that one. And I know the factors are 1, -2, -21, and -18. And I should be able to do this pretty quickly. And look at that. The -3 works. I ended up getting a 0. That's perfect. And that means after the first round of division, my factor was x plus 3, and I ended up with x squared minus 5x minus 6. And I can go ahead and take that x squared minus 5x minus 6, and I'm going to factor that the rest of the way. And again, because I have this x squared minus 5x minus 6, I do have a little bit of help because I already looked up the zeros. I can say, hey, well, one of the zeros was a -1, so I should do an x plus 1 up here. And one of the zeros was a positive 6, so I should do an x minus 6 here. And that'll get me my factors really fast. Okay, and then once it's all done, I can say f of x equals x plus 3, x plus 1, x minus 6. There's all of my zeros in factored form. All right, and then this problem, though, just make sure we're answering the question. It asks us to find the zeros, not the factored form. Like the first problem asked us to write it in factored form. Whoops. This problem actually asks us to find the zeros. So the zeros would be x equals -3, -1, and 6. So we can find them graphically. That's perfectly fine. It might save us some work on the division, so we don't have to guess a bunch of times till we find one that works on division. All right? But we still need to be able to show algebraically how to simplify the expression. It's really important that you understand how to do that algebraically. All right, one more example here. Last one for today. Find all of the solutions, all right, for x to the 4th, okay, and this time it says solutions. That means our answer is going to be f of x equals y. We're going to have to find out what those values are, or I'm sorry, f of x equals 0. That's how we're going to write our solutions, okay? So we're starting with a -15 here. So the possible zeros like what we started with at the beginning. Positive, negative 1, 3, 5, and 15. So there's 8 possible zeros. But this time, this is a 4th degree polynomial. So 4 of those 8 zeros should work rationally, right? 4 of those 8 should work, theoretically, to get rational zeros. All right? That's what we're hoping. But let's go ahead and double check on our graph, just because we know we can do it on Desmos. I'm looking at the graph. The most is 4. X to the 4th minus 2x, whoops, no capital X's, 2x cubed minus 10x squared minus 22x minus 15. It's a lot of x's that are capitalized. Whoops. All right, there we go. Here's my graph. And if you guys notice, there's actually only 2 rational zeros here. Negative 1, 0 and 5, 0. That means that our other 2 zeros are going to be imaginary zeros. We would deal with imaginary numbers there, which we technically don't need to worry about in this class, which is nice. But this helps us get an answer to our question too. It tells us once we get down to a quadratic, we're not going to be able to factor it anymore. We can leave it in factored form. All right. And we don't have to worry about factoring it anymore because it does ask us to write this answer in factored form as well. So I'll explain that when we get down to it at the end. So one of the zeros we have is negative 1 and the other one is 5. I'll write those down. So we'll start with negative 1, and we're going to say 1x to the 4th minus 2x cubed minus 10x squared minus 22x minus 15. And we should get a 0 at the end here. So we get negative 3 there, we get a positive 3, negative 7, positive 7, negative 15, positive 15, 0. Perfect. So there it is. We've got the first one factored. And what happens is this was a 4th degree polynomial, and we used polynomial long division, and we factored out, used the factor x plus 1 to get it from a 4th degree down to a 3rd degree polynomial. Now, we have to take this 3rd degree polynomial here, and we're going to divide again. So this time we're going to use the other 0. We're going to use the 5. And we say negative 1, negative 3, negative 7, negative 15. And that's going to help us get down to a 2nd degree polynomial. So we just use the numbers that we just finished, and we do the division one more time. 5 times 2 is 10, gives us a 3, that gives us a 15, and a 0. Perfect. So now, after that, I've said, okay, one of the factors was x plus 1. The other one was x minus 5. And finally, I had x squared plus 2x plus 3. And by looking at my graph, I already know that that cannot be factored anymore. That is as, oops, sorry, I didn't switch the screen back. So we're still looking at the graph, but we see those 2 zeros. All right. So what happens then is I did the polynomial long division on the of negative 1 of the 4th degree polynomial, and I got a 3rd degree polynomial down here. That's what the this is what the output was of that division. And then I took those values and I did the division again with the other 0, which was the positive 5. And now I've got it down to a 2nd degree polynomial, x squared plus 2x plus 3. Because on my graph, I only saw 2 zeros, 2 x-intercepts, I know this is in factored form. Like if I used the quadratic formula on this because I can't just simplify it, I would get imaginary solutions. Because I looked at the graph. So that's part of our solution. That's factored form. The other part of our solution, I have to write my solutions. Well, there's f of -1 equals 0. F of 5 equals 0. That's how I write my solutions. Okay. So find all the solutions and write it in factored form. So there are two real solutions, and that's what they are. We don't need to worry about finding imaginary solutions right now. Just the real ones. Okay, if you were in accelerated algebra 2, I'd ask, or accelerated AGS3, I should say, I'd ask you to find the real solutions. Or the imaginary solutions as well. All right, but that kind of covers everything for today. What we're doing is we want to identify the possible zeros. So on every problem, list all of the possible zeros. List all the possible zeros. And then if you want to, you can use Desmos. If you don't want to use Desmos, you can do the guess and check method for each of these problems. All right, but some of them might be a little tougher. Like for example, 24 is going to have a lot of factors. 56 is going to have a lot of factors. So it's not a bad idea to go and do the guess and check. For each problem, I want you to write each one in factored form. And I want you to list the zeros of each function. All right, so factored form and the zeros of each one. All right, it's 8 problems on your assignment. We've got 20 minutes left in class, so that's plenty of time for you guys to get started on it right now and honestly make a pretty decent dent in it. All right, but if you have questions on anything, please let me know.